All right, good morning. Let's start the class. All right, today's topic is about called line integrals, and more precisely should call it curve integrals. This is a line usually means straight lines. Okay, so yeah, integrals along curves. Okay, more precisely, I should say integral along curves. Okay. So in the space, if we have a curve, right? And for example, this curve maybe the density function is not the same. Okay, the density changes on the curve. So questions, what is the weight of this curve, right? This object. Then it involves integral along the curve. Okay, you have to integrate the density function on the curve. Now, how do you do that, right? So, another things, if you have just want to measure the length, okay, and also you want to, for example, if you have a temperature function along this curve, and question how do you find the average temperature around this curve, right? So this is what so this can be a two-dimensional curve, or could be curve in a three-dimensional space, or could be in two-dimensional space. I'm not going to specify. So the idea is very simple. Suppose you have a function, let f be a function along, this is a function along the curve C, okay? And this is the curve C. And then we want to find out the total value of the f along the curve C. Okay, if you divide it by the length, then it gives you the average value. So this function can be a temperature function, can be density function, right? So we want to find the total value of the f along this curve C. How to define that? So the idea is very simple. You partition this curve, okay? So you have P0, P1, P2, P3, and the last one is Pn, okay? Then you choose an arbitrary value, choose an arbitrary point in each interval. This is a, So if this is a pi minus 1 pi, then take an arbitrary point here, pi star, okay? So the total value that would be the f pi star, right? The value of that particular point. You multiply it by the distance between pi and pi. Okay, so you add them together, from 1 to n. Okay. Yeah, and that gives you, this is a distance. Okay. That gives you the approximation of the total value for f. Okay. Now, on the other hand, this one, let's look at that. So this, if f is constant, okay, if f is constant and 1, then you end up with just this one. Okay. Remember, this is approximation of the length of the curve. So the limit will be the length. So this one is the length of the curve. Okay, that's the limit. Okay, so if but this one, how can I describe the limit? The limit is going to be denoted as this notation, f and the ds. Okay, that's called the integral of f. Yeah, and this is also a special case. The integral S is the arc length. Okay, the integral of 1 around the curve. Okay, with respect to the arc length. Okay, so ds is a arc length. Okay, this is a what do we have here? Okay. Right, so question is how do we calculate? How do we calculate this? Okay, so if the if the curve is parameterized, by a function, okay, by function. Okay, so this is a x equals x of t, y equals y of t. Okay, and t is between a and b. Okay, in that case, the point, right, pi is going to be xti, yti. Okay, right? Can describe like that. And you have a t a equals t0 and t1, tn, that's a b. Okay. And the distance pi minus 1, right? This is going to be the length of r, the length. Yeah. Now this actually can be approximated. Okay, this can be approximated by ti star, the length, and the delta ti. Okay, so I'm going to show you why this is true. Okay. Why this is true? Okay, this is I as r over t is going to be, it's going to be x over t, y over t. Okay, the reason is this is going to be the length, the distance, right? The square root of xti minus 1 minus xti square plus yti minus 1 minus yti. Okay, right? And then you can divide both sides by you can divide by delta ti here. Okay, so you put the delta ti here, then you put it inside, and this will be under this. It's delta ti. Okay, and then this is about by there was a theorem. This is about the derivative of something ti star, right? Approximated by the mean value theorem, right? So this is almost equal to star ti, some point, okay, square, and this is y prime ti star. Now that's slightly different number, okay? It's not necessary to the same ti star. So you have double star, but that's okay. But then, because this is arbitrary point, so you can take an arbitrary point, ti star, so square, and y prime ti star square, okay? Delta ti, just approximation. So this is a nothing but the length of ti, the derivative. Okay, so that's why the above approximation here's a let me check. Let me put it. So the above approximation f pi star and pi minus 1. Okay, this is approximated by, this is a r ti star, right? And this is a length of the tangent vector at some point, and delta t. Okay, then it's clear that the limit, okay, the limit is going to be the integral of from a to b, f of r over t, and this is r prime t, the length, and dt. Okay. So now, okay, so now we have the following formula. Okay, the integral of the function around the curve C is going to be, can be calculated by, can calculate by this formula. Okay. All right. So what is this? This actually is called a ds. Okay. So the differential of the arc, the differential of the arc length. Okay. ds is actually going to be that. Okay. So the integral of this is going to be the arc length. Okay. So if you have a curve here, that's a starting point, s equals 0. That's the point S, right? Then S is going to be integral from at the point T, and that is going to be integral from A to T, tau and d tau. Okay, so that gives the arc length. It is the arc length of the curve. All right. All right, so if you are given a function along the curve, how to evaluate the integral of the function along the curve? That gives the total value of the function along the curve. You need to find the parameterization for the curve. And that curve could be in 2-dimensional space, could be in 3-dimensional space. And that's it. It doesn't matter which parameterization you choose for the curve. Okay, and you always get the same value. Okay, you always get the same value. All right, so let's take a look at a function. Yeah, let's look at the following example. Okay, as the function, here's a function. Okay, the function is defined on the xy plane, so it's 2 plus x squared y. Okay, the curve is the up half of the unit circle. Okay, the half of the unit circle, x squared plus y squared equals 1. Now, the function is not only defined along the curve, the function is defined on the whole, in the whole plane, but it's can be restricted to the curve, right? So we want to evaluate the integral of function as a restriction of f on this semicircle. Okay, so this is also in some usually it's also written just 2 plus x squared y ds. Okay, that can be written like, okay. So that means the value of the function is 2 plus x squared times y at the point x and y. Okay, and if the point is on the circle, then the value of the function at that point is 2 plus x squared y. Okay, actually the function here is defined everywhere. It's not only just as a circle. Okay, but we want to find out the total value of the function around the circle. Okay, so how to do that? Well, it's very simple. All you have to do is to find the parameterization, which is cosine t, yt equals sine t. T is between 0 and pi because it's a semicircle, right? And here, yeah. So that's it. Then you find out that you have to find out r prime, right? R prime t is going to be, now this is well, you can write down the formula directly, but let's use write it as a vector equation. Okay, r over t is going to be cosine t sine t. So then we differentiate, it'd be negative sine t and cosine t. Then, okay, then ds is going to be the length of the tangent vector multiplied by dt. Okay, so which is going to be just equal 1, so just dt. Okay, it's the same. Okay, because the length, this is unit vector r prime t, the length is going to 1. It's obvious. Okay. The curve has right now the orientation does not play any role here. Okay, orientation. No, we don't consider. You can choose any arbitrary. The curve, we don't mention what is the starting point, what is the end point. Just have the same circle. If you start from the other end, you end up with the same result. Okay. Yeah, think about find the length of the curve. Doesn't matter which orientation, which is starting point, which is the end point. So find the total value of the function along the curve. I don't think this should depend on the orientation of the curve. Okay. All right. So now the total value of this function, f, is going to be the integral from 0 to pi. So here's the f of, so the restriction of the function, right, to the curve. Right now, x takes cosine t squared, y takes sine t, and this just ds is just dt. Okay, so just evaluate this function. Okay, so the first function, the first one is just a 2 pi, right? The second one, I have to use a substitution. Okay, so use substitution, you left u to be cosine t. So du equals negative sine t dt. Right? Then it's 2 pi plus, when t equals 0, I get a 1. When t equals pi, I get a negative 1. It's u squared, and sine t dt is negative du. Okay. So I should get positive value. Okay. I change the order, then I get rid of the negative sign. Okay. Then the antiderivative of this will be 1/3 times u cubed from negative 1. Okay, and the answer will be clearly will be 2/3. Okay, so that's that is answer 2/3. Okay. So let me repeat again. If you have a curve, if you can use a vector equation to describe curve, t is from A to B, and that's called curve C. Then the integral of this is just the integral from A to B, f, the value of the function around this curve, and this will be, this is my ds. Okay. So that is it doesn't matter in which space dimension space. All right, so let's continue to do some problems. All right, let's take a look at some examples from the book. This is okay, here's a problem number 6. Okay, this is the integral c e to the x d. Now it's too early. Let's look at problem number 4. Okay, so it's going to be x is to the y, e to the y, and the ds. Okay, and the c is the line segment from the point 2, 0 to the point 5 and 4. Okay. So this is in two-dimensional plane. Okay, so you have a 2 and 2 and 0 is here, right? And the 5 and the 4 is here. That's just straight line. Okay, that's a straight line. That's a C. And x times e to the y, right? So we have to, first of all, we have to do is to find the parameterization. Okay, find the parameterization, find the vector equation for this line. So the idea is, the trick is that this is a vector, the first vector, 2 and 0, plus t times the last vector minus the first vector. Okay? Then you will see that when t equals 0, you get the first vector. When t equals, okay, for strict line, it's easy to find. Okay, when t equals 1, you get this the end point. Okay, another end point. So you can simplify right now. It's a little bit, right? It's going to be you can do like this. Yeah, 2, 0 plus t, 5 minus 2 is 3, 4 minus 0 is still 4. Okay, so when you differentiate, you only get 3 in this point. Okay, all right, so we got the length is going to be 3 squared plus 4 squared, just 5. Okay, it's constant length. Okay, all right, now the integral of the c of x e to the y ds is going to be integral from 0 to 1. X is going to be replaced by 2 plus 3t. Okay, y is going to be replaced by 0 plus 4t, so it's just 4t. And the ds is 5 dt. Okay, so that's it. Then you have to evaluate this integral. We needed to find the antiderivative of the function. So the first one, e to the 4t dt, the antiderivative is going to be 1/2 e to the 4t. Okay, that's obvious, right? And 2 divided by 4, that's 1/2. Now the integral of the 3t e to the 4t, we have to use the integration by parts to find the antiderivative. Okay, so how can I do? Well, it's a 3t, then I have to express as a derivative, right? Okay, then that'll be 3t e to the 4t e to the 4t in the 4, and switch the order, right? And that is going to be e to the 4t, and it differentiates 3t gets 3. Okay, you can do that, right? It's an integration of parts, and then you can find the antiderivative. Here 3 e to the 4t should be 1 of 4 times e to the 4t, that's 16. Okay, so we get the antiderivative of each of the function. Then we can evaluate. Okay, so the antiderivative of the first one, then antiderivative of the second one, the antiderivative of the fourth, last one, and evaluate 2 endpoints. Okay. The first one you will get when t equals 1, you get 1/2 e to the 4. That's 3 over 4 e to the 4 minus 3 over 16 e to the 4. And the last one will be plug 0. Every term is 0, so it's going to be 1/2 minus 3 over 16. Okay, and then you simplify. Okay, then you simplify. Well, how do I simplify it, right? I need to do a little calculation here. So 1/2 is 8 over 16. Okay, minus 12, plus 12, minus 3. So 20 minus 3 is 17 over 16. Okay, so it's going to be 17 over 16 e to the 4 minus 5 over 16. Okay, so 8 minus 3 is 16. Okay, so that is answer. Okay, yeah, not too bad. Now, now we were going to we're going to define the integrals of vector fields along a curve. Okay. Okay. So if we have a curve in the space, at this time the orientation is important. Okay. So this is starting point, this is the end point. So you have a vector field in the space. Okay, that's F. Maybe the vector field just around the curve. Okay, maybe just along the curve. You don't really need to know the vector field away from the curve. But at every point, there's a unit tangent vector here. Unit tangent vector here. Okay. Okay. So this T is a unit tangent vector. Okay. It is in the same orientation as the curve. Okay. Then you have the inner product, right? Then F T, okay, is a function. Is a function along the curve. Do you agree, right? Along the curve. Then you can integrate this function. So then you have C, F dot, T, and the ds. That is called the vector. That's called integral of F along curve. Okay, it is called the integral of F around the C. Okay. F itself, I cannot evaluate the integral, right? But the inner product is at every point is a number, so it becomes a function around the curve, and that function can be integrated, right? It's called, right? So after you define the integral of the integral of a function on curve, then you can define this one. This is actually a special one. Given vector field, you get a function along the curve. That function is defined as the inner product of the vector with the unit tangent vector. Okay. So how can I describe that? Okay. So if you know the arc length S, okay, then if we can describe F, the dot product as a function of S, then you integrate with respect to S. But in general, you're not lucky. You cannot even find the arc length, okay, using elementary function. So I just take an arbitrary parameterization. This is a vector equation for the curve. Okay, T is from A to B, and how can I evaluate? Okay, first of all, at that particular point, okay, the value of the vector, you can see that, right? So you at that point, this is a vector, so it's a value, right? Yeah. And how can I describe the tangent vector at that particular point? The tangent vector, okay, if I differentiate R, right, I probably get pretty long R prime T here, right? So if you want to get tangent vector, you have to normalize it. the tangent vector at that particular point is going to be right, the unit tangent vector. Right. So now it's clear, right? So let's try to figure it out. So f integral ds is going to be, I change it to a to b, right? This is f, okay? And the tangent vector, okay? And then this is the function. Then ds, I remember, right, is the length times dt. So that's a ds, okay? This is a f, this is a t, okay? Right? So, but you will see that the length of the tangent, length of r prime is cancelled out. So you can simply get okay, right? Because this is a cancelled out. Good. And this can be also simply denote, yeah. If we I change the notation a little bit, right? So if I denote this as r prime t dt, okay, just differentiate, right? Then this part can be replaced by, okay, can be replaced by dr prime, I put a t here, right? Yeah. But if I want to remove the t, then I can still go back to the c. I can simply write in this form. Okay. So those are the notations. Now we know how to evaluate this integral. Now, if on the xy plane, right, in the xy plane, if that's special case, this is a function defined. I have two components. Right? If it's in the two components, and r prime t is going to be x dy over t, right? Then we have right? I don't need to find the landscape. So the integral and t is from a to b. The integral of this I don't want to, yeah, if just a c here, then okay. Integral of this ds, right? Is this the same notation as if you choose a parameterization? If you don't want to measure the parameter t, this is another notation. Okay. Now, if you replace the by, if you use a variable t, then from a to b, f evaluate this is going to be p x of t y over t, right? Q x of t y over t. Okay, and the inner product, and that is yeah, that is a r prime, right? So this is f, and this is r prime t, right? R prime t is a x prime t, y prime t, and then dt. Okay, but this is inner product, so I can even multiply them out. That if I multiply them out, I get p x of t y t x prime t. Okay, then q. Okay, that's it. Okay, so you can evaluate this using this formula. Okay. Now, I also want, that's for that's for the one on the left hand side. For the right hand side, remember, if I let the dxt to be x prime t dt, okay, dy and the y prime t dt, okay, then dr is going to be just dx dy, okay, which is x prime t, y prime t, and dt, okay, which is r prime t dt, okay. Then above formula, okay, it's going to be also written in the form dx dy, okay. And if f, it has a component p and q, okay, then you can write p dx q dy, okay, the inner product. Okay, so when we see, sometimes if we only see one component, okay, so if we have a function, okay, so this is a function, if we just only see a function f dx along the curve, this actually really means the function this is really means actually is f dx plus g dy, okay, and g is 0, okay. So then, in other words, this is actually the integral of vector field along the curve. Okay, this is going to be f0 dot dx dy. Okay, okay. So this is actually is the integral f ds. Okay, and that f the vector field is just have a one component. Okay. Okay, we understand that. Then we can do the other problems. Okay, so here's a problem number . Okay, so I'm going to do the problem here. Evaluate the integral of c. Okay, it says that x dx plus y dy. Okay, and where c is up semicircle from 1 0 to 0 1. Okay, sorry, not from 0 to the negative 1 and 0. Okay, so the orientation is given. The orientation is given. Okay, so that's a C. Now, how do we solve this problem? I think all we have to do here is very simple. Just let x to be cosine t, y to be sine t. Okay, so dx is just x prime dt. Okay, so dx is a negative sine t dt, and dy equals cosine t dt. Okay, so this integral is just from 0 to pi, x is cosine t, and this negative sine t dt, plus y is sine t, then you have a cosine t dt. Then you find out, add them together, you get 0 and dt, so the answer is 0. The answer is 0. Okay, now this above integral means what? This above integral is actually if you let f to be xy to be x and y, right? And then this above integral is actually going to be the integral of f, okay, times the t ds. Okay, you understand that? Then you can see that. Okay, then you will see. Let's look at this curve. So the tangent vector, the vector f, right, at this particular point, x and y, this is a f. Okay. What is tangent vector? Tangent vector is in that direction, right? Unit tangent vector in that direction. This is the perpendicular to each other. So clearly, this is always 0. Clearly, this is always 0. Okay. Clearly, this is always 0. It's a product. Okay. That's why the above integral is going to be 0. You see, I can get this in a different way without using, without even differentiating. Okay. Yeah. Okay. Yeah, because it's always perpendicular. The vector field is perpendicular to the curve at every point. And the function you're supposed to get is the inner product of the vector field with the tangent vector. And this is always 0. So that's why integral. Okay. Okay. So let's take a look at the next problem, which is 20. Okay. It's in 3-dimensional space. This function is defined x plus y squared and xz and y plus z. Okay. And the curve is parameterized by this one. So it's t squared. No, this is 20. So t squared, t cubed, negative 2t. Okay. T is between 0 and 2. So you are given the parameterization for the curve. Alright, you don't need to sketch the graph here. Just you can, if you want, you can put a starting point in 3-dimensional space. As a starting point when t equals 0, it's here, right? At the origin, when t equals 2, x, both x and y is positive. It's like that, and then but z component is again negative. So this is a c. Okay, the starting point and end point c. So we want to evaluate f dot dr. Okay. Or this is the same notation as this. Okay. T is here as a unit tangent vector. ds is arclength. Okay. And this one is written again. If f has 3 components, will be x plus y squared, and dr is dx dy. Right? Dr can be dx, dy, dz. Okay. So that'll be dx, xz, that'll be dy, and at y plus z, that'll be dz. Okay, so this also can be written in this form. Okay. Now, you have to use parameter t to evaluate integral. So if you use a parameter t, and t is from 0 to 2, right? What is my x here? X is t squared, so t squared. Y is t cubed. T cubed and the square is t to the 6. dx will be 2t dt, okay? That's the first term. The second term, x is t squared, z is negative 2t. dy is 3t squared dt. Okay, that's dy, that's dx, that's dy. Okay, and the last one is y is t cubed, z is negative 2t, and dz is going to be negative 2 dt. Right? So you have to combine them, all of them, right? So I'm going to get 2t cubed and 2t to the 7th, and here negative 6 and t to the 5th, right? And I also have a negative 2t cubed plus 4t dt. It's a very complicated function. Okay. Yeah, it's a very complicated function. Okay. So the only term you can simplify t cubed is canceled out. Okay. So now the antiderivative of this is 2 over 8 t to the 8th power minus
6 over 6 to the 6 plus 4
over 2t squared, and evaluate 2 endpoints. Not too bad, right? A quarter 2 to the 8th power minus 2 to the 6th plus 2 times 2 squared. Okay, it's not too bad. Okay. Can we simplify a little bit? Yes, the first term is t to the power 6. Right? Yeah. 4 is 2 squared. That's why minus 2. The answer is 8. Answer is 8. All right. Okay, now let's look at number 8. Yeah, let's look at number 8. So evaluate this integral, okay, where C consists of the arc of the circle, okay, x squared plus y squared equals 4 from the point to this point, then followed by the line segment, okay, from 0, 2 to 4 and 3. Okay, so we have to sketch the curve first. Okay, so this is a curve, 2 and 0, and 0 and 2. So this is a Okay. So this is a curve, right? Then from 2, 0.2, 0 and 2 to 4 and 3. So somewhere here. It goes like that. There's two pieces.